Okay, so I'm going to quickly go through the internals of Apache Spark and give you a quick introduction to Spark ML. Okay, this is going to help you really, truly understand what you are doing in the assignment. Okay, and then we will have plenty of time for a Q&A and Elena to walk through the instructions. So yeah, this is, we're going to basically cover distributed computing, and Apache Spark is a compute engine for clusters. And we will look at certain data structures that are available in Spark, the Spark framework, called RDDs and data frames. RDD is a resilient distributed database, and an evolution of RDDs is data frames. After that, I will give you a quick introduction to machine learning with Spark, and we will look in some detail the concept of transformers, estimators, and pipelines. And if there is time, I will discuss one example, which is gradient descent. Otherwise, we will just continue with code walkthrough. Okay? Now, if you have any questions, you can post them to me or to the whole class. I'm listening on the chat. Okay? So, now if you have studied last week's materials, watched the lecture, you should be very familiar with Mapreduce. Okay, this was the first and a sort of primitive computational technique or strategy that was used on HDFS. Okay, there are clearly two parts to this computational paradigm. One is map, and the other is reduce. And you should be familiar with this slide. I explained all the operations in some detail last week. So I'm going to very quickly refresh these concepts so that you can understand the difference between MapReduce and Spark. Okay, Spark was actually a generalization of MapReduce, and so it's quite useful to start with MapReduce. Okay, so on the left I have shown 4 compute nodes. Okay, as examples, there are 4 compute nodes, and the file that is that has the data, structured or unstructured, is distributed across the cluster, and it is stored in HDFS. So what happens during a MapReduce operation? Okay, let's say you're doing a word count, or something similar, or a k-means clustering. Then the function that you write in the mapper class is going to be shipped to all the nodes that have the required data. Okay, so you know that the file, if it is a large file of textual information, it is chunked up into blocks of 256 MB, replicated 3 times, and stored across the cluster. Okay, and so you have to find at least one version, at least one replica for each block, and ship the mapper function to that particular node. Okay, and the mapper is used to locally compute results on that data. Okay, so you don't move the data to the computation, you move the computation to the data. Okay, so let's say you are doing either a word count or k-means algorithm, k-means clustering. Then the function is going to take key value pairs, and it is going to emit intermediate key value pairs. And I have shown some of the, I have shown examples on the right-hand side. Okay, so each table you see here is has a lot of key value pairs. And, this is the result that comes out of the computation. Initially, these results will be stored in memory. And as the memory buffer starts filling up, it will be spilled into the disk. But how it is spilled into the disk depends on what kind of classes you have written to follow the mapper class. So, for example, you can write a partitioner and a combiner, and what they will do together is further chunk up the results into smaller files. Okay, so the partitioner will take all the results computed by the mapper, and it will apply a hash function to each of the key values. Okay, so what does the hash function do? It just translates the key value into a number, and then that number is divided by the number of reducers. Okay, let's say we have 500 reducers. What will be the output of this operation? Okay, let's say you take the key value, pass it through the hash function, and then you divide it by 500. Okay, the result will be a remainder from 0 to 499. Okay, so there will be 500 distinct remainder values. Okay, so I've assumed that we have two reducers in this example, so I am dividing the output of the hash function by 2, and I'm calling them 1 and 2. Okay, so when a row has a remainder of 2, okay, which is shown here in red, that means the data in that row needs to eventually go to reducer number 2. Okay, so now the partitioner computes these remainder values, and then it segregates the rows into two smaller files. Okay, the first file has all the key values that will result in a remainder of 2. The second file has all the key values that will result in a remainder of 1. So the first file then has to go to reducer number 2, and the second file has to go to reducer number 1. Okay. Now, within each one of the subfiles, you will often have the same key value repeating several times. If you use a combiner, okay, that key value will be grouped together, and you can see that in this example. Okay, so you have two K4s, they are combined together, and you have the values added up here. Okay, that's the function of the combiner. So this is what spills the data into the disk. Okay, there is not enough space in the buffer to hold all these results. So these files are stored on the disk. Okay, so imagine if you have 1,000 mappers and 500 reducers, you're going to have 500,000 small files that have to be stored in the disk, and then they have to be shuffled over the network to reach the corresponding reducers. So that takes a lot of time. Okay, now you will see that Spark does a lot of innovations to reduce this time. Okay, the time taken to chunk up the results into a large number of smaller files, and the time it takes to shuffle this data across the network to the reducers. Spark is going to try to reduce both these times, okay, both these latencies. So, and once it is the data are shipped to the reducers, you have the reduce operations. Okay, now if you have to repeat this process iteratively, for example, if you are doing k-means clustering, okay, you have initially set 10 centroids. Okay, each mapper is going to act on each point, and it's going to emit a key value pair. The key will be the point, and the value will be the distance from each centroid. Okay, So you have done one iteration, and then you can recalculate the centroids, and you go through the second iteration. And remember that you're going to have tens of millions of points, okay, and tens of millions of records, okay, and you have to repeat these iterations till the centroids don't move much, okay. You know this from your previous courses. Okay, so how do you use MapReduce to accomplish this? Once the first set of distances from the centroids are calculated, you have to store all the data again in HDFS. That's going to take time, right? You have to store new files into HDFS, and then you restart the MapReduce again for the second iteration. And you know that typically, K-means algorithm can take anywhere from 100 to 1,000 iterations. So remember, just think about all the overhead involved in iteratively computing the centroids. Okay, so this is exactly why MapReduce was not very efficient. Okay, so we come now to Spark. You may already know that the initial work on Spark was done at UC Berkeley, and this is the title of the paper published by the creators of Spark, Resilient Distributed Data Sets, a Fault-Tolerant Abstraction for In-Memory Clustering. Okay, that was the title of their paper. And you see the first author, Matej Zaharia, was the primary person involved in developing Spark. And you know that the company now that is mostly involved in advancing Spark and cluster computing is Databricks, and Zaharia is the CTO of Databricks. Okay, so he's continuing this work in Databricks. So that's a little bit of history. You can actually, Zaharia has written a lot of books on Spark. You can read them online, and you can also watch a lot of lectures by Zaharia on on Spark, as well as the roadmap for the future roadmap for Spark development. Okay, so what is the main distinguishing feature of Spark? As I said, Spark is a compute engine for clusters, the data stored on clusters. So here you see 4 nodes. These are the 4 columns. Okay, and let's assume that you have 4 different data sets stored across the 4 nodes. Okay, the first data set has 3 partitions. Okay, partition 1 is in node 1, partition 2 is in node 2, and partition 3 is on node 4. Okay, now if you are running a MapReduce test, okay, you don't control these partitions in real time. Okay, you say what MapReduce does is it ships out the map function. It goes locally to each one of those nodes, and all the computations take place there, and the results are returned to some other node. Okay, which is running the reducer function. Okay, during this process, you have no control over these partitions or these data. Okay, what the main feature of Spark is that it gives you an abstraction called an RDD. Okay, a resilient distributed data set. Okay, what it is a wrapper, kind of a wrapper around these partitions. Okay, so you no longer need to think of these things as individual blocks or replicas distributed across the node. but this is a data structure, okay? It's a data structure, just like an array or a list, okay, or a vector, or a cell. It is a data structure. An RDD is a data structure, okay? So there is this singular abstraction that Spark gives you, okay, which holds all the data you are trying to manipulate and compute, okay? So you have now four different RDDs. Those are, again, four different data stores, okay? So that is the main, that's one main feature of Spark, okay? Now, so here you see how computation happens in Spark. You got the executor JVM, so this shows you the memory. All these different partitions are stored in memory, and this is an RDD, okay? And these are the CPUs. The map task transforms them into, again, results that are stored in memory. And then, okay, here you see sort and spill, okay? Now, this is just one example of how this thing is executed. This is what happens in Spark 1.4, okay? Now, we have moved away from it, but I want to tell you how this improves over Mapreduce, okay? So remember, in Mapreduce, you had partition functions, okay, and they were generating lots of smaller files. Here, that does not happen, okay? Instead, what happens is the data from each mapper is sorted and spilled into the disk, but it is not chunked up into smaller files. Instead, you have a single file, okay, one single file, output file from each mapper, and then you ship it across the network, and you merge the files in an intelligent way, okay, so that you don't need to separate out the files or the rows by their key values. Okay, so I'm giving you an example here. Let's say you're doing word count, and the first set of results look like this. Okay, the letter A appeared 936 times, AB appears 6 times, and so on. Okay, what this is a binary heap. Okay, it is a binary heap, and it can be ordered by either the key values or the values. Okay, either the keys or the values. So here I have shown a binary heap ordered by the keys, okay, and that is each output file. And you can do some highly optimized merging, okay, at this level, okay, so that you combine the key values and you do the reduce operations in a shorter period of time, okay. This is an example of what Spark does. Okay, if you ask people generally, how is Spark better than Mapreduce, they will say it's in-memory computation, it has RDDs, and things like that. That is true, but behind the scenes, Spark optimizes almost every operation. Okay, every sort operation, every it optimizes the spills, the merges, okay, it does a lot of that, and that's how it saves time. It saves computation time, okay. So this is very important and an often overlooked feature of Spark. Okay, Spark is not just a simple generalization of Mapreduce. What these guys do often is, they do a lot of research, they do lots of simulations to figure out what techniques save time, reduce computations, and things like that, and then they implement those techniques into the framework, okay? So, so these are the main features of Spark. Apache Spark, as I said, it is a generalization of Mapreduce. especially suited for iterative computations. And these are the 6 things you need to remember about Spark. Okay, it has specialized data structures, 3 of them, RDDs, data frames, and data sets. We'll look into them in detail. There is, of course, in-memory computation, and Apache Spark uses DAGs, or directed acyclic graphs, that optimize computations. Okay, and there are 2 types of computations allowed in Spark. One is called transformations. These are also called lazy evaluations because the transformations are not executed as soon as you apply them. They are only executed when an action is triggered. Okay, actions are actually the functions that produce outputs. So when you trigger an action, then Spark analyzes all the DAGs associated with the transformations, comes up with an optimal computational strategy, and then starts computing. Okay, and the 4th point is what I explained just now. It optimizes all sorts of sorts, merges, and shuffles. You can see, Databricks and UC Berkeley have published a lot of papers on, how they were carried out these simulations. And then Spark also provides a very rich set of APIs in Scala, Java, Python, and R. You will be mostly using Python, I guess. But, you can also easily switch to Scala if you want. And it has a number of APIs for machine learning, SQL, streaming, and graph. Okay, so those are the 6 things that you really need to know about Spark. Okay, so I mentioned transformations and actions. Transformations are the, are also called lazy evaluations, and actions are the ones that actually trigger computations. Okay, so now let's look at transformations in some detail. Okay, so there are 2 types of transformations. 3. One is narrow dependency transformation, and the 3rd is shuffle. Okay, so you can see the examples of narrow dependency on the left side. Okay, each small square is one partition, and each rectangle is an RDD. Okay, so here you have 2 RDDs. Each RDD has 3 partitions. Now, if a operation or a task, okay, happens in such a way that there is at most one partition of the child for each parent partition, then that is a narrow dependency transformation. Okay, so you can see this is partition 1, 2, 3, partition 1, 2, 3. Okay, this partition, okay, uses the first partition from this RDD and the first partition from this RDD. Okay, so these 2 are coexisting partitions. They are probably on the same node. Okay, so when you do a join like this, you have 2 RDDs and you're joining them together. Okay, but the join is a special type of join where each partition comes from only the co-partitions. Okay, so then that is a narrow dependency. Okay, that's called a narrow dependency. Here, each partition transforms into itself. Okay, so this is when you do operations like map and filter. Okay, what happens is the data in each partition, okay, is transformed and stored in a partition on the same node. So there is nothing that is being shuffled across the network. Okay. So this is another. These two functions are also examples of narrow dependency transformations. Okay. Here you are doing union. Again, this can be a narrow dependency because all you are doing is gathering all the data in these two RDDs and you're putting them together in a single RDD. Okay. So join with co-partitioned inputs, map, filter, union are all examples of narrow dependencies. Okay. When you do group by key, then that's going to be a wide dependency operation. Okay. Why? Because the same key could be in the first, second, and the third partition. Okay. Let's say key number 1 could be here, here, as well as here. So all of those rows, records have to be shipped to the first partition. Okay. If you're going to group by key. So that's why it is a wide dependency operation. Similarly, if you do a outer join or a left outer join, for example, between two sets of data, let's say these are customer records and these are orders. Okay. If you're doing an outer join to see all customer and orders, all customers and orders together, then that's going to be a wide operation because you got to ship, you have to join the customer list here with customers here, with orders here as well as orders here. Okay, so it's going to be a wide operation. Okay, so that's those are the two main things you need to know about transformations. And here I have listed. Okay, let me just give you this list first. Okay, usually these transformations have narrow dependencies. So these are maps, flat map, filter, and so on. These transformations have wide dependencies, and you can see here left outer join, right outer join, that kind of stuff. Okay, so let me stop here and see if there are any questions. Does anybody have any questions? I'm going to take after Rena's example and start asking questions if there are no questions. Do we have any questions so far on RDDs? Is anything not clear or do you understand how you can use, how transformations and actions are used in Spark programming? Okay, so let's continue. I'm going to give you a simple example and illustrate, both wide and narrow transformations. Okay, so let's assume that a big store like Amazon wants to know how many shippings were done for payment during a certain period of time. Okay, it just wants to know total number of shipments. Okay, so there are two categories of members. There are prime members. If it was a free shipment, okay, so we're gonna call that 0, the value 0. If it was a paid shipment, then we need to count that shipment. Okay, so paid shipments have a value of 1 and free shipments have a value of 0. Okay, and for other members, non-prime members, every shipment is paid, so all the shipments will have to have a value of 1. And then we just add up all the values across all the members and all the orders, okay, to get the total number of shipments. Okay, it's so now let's look at RDDA up here, and these are non-prime members. Okay, so you got customer 1 with a bunch of orders, and those are stored in partition 1. Customer 1 also has other orders that are stored in partition 3, and so on. Okay, so these partitions contain all the shipment data for all customers who are not prime members. Okay, so the first thing you will need to do then is a group by operation, because you want to calculate the total number of shipments for each customer. Okay, so when you do that, obviously customer 1 data, okay, will have to flow here, and it also has to come from the third partition and flow into this partition. Only then you can sum up the total number of shipments for customer 1. Okay, and now in RDDB, you have all the total shipment numbers ordered by the customer value, which is the key. Okay, so remember that once you do a group by operation, all the results are going to be already ordered by the key value, the key, okay, which in this case is the customer ID. Okay, now let's go to C. C are all the members, okay, all prime members, some of whom had free shipments. Okay, so what you need to do with C is take the RDDC and you apply this map function. You're going to map each customer to a tuple, okay, with the customer ID and 0. And the resultant RDD is D. E is all prime members who paid for the shipment. Okay, so here you just emit the same values. Okay, they already have a shipment value of 1. Okay, and then you need to do a join to get the total shipments for all the prime members. Okay, and when you do that join, you're going to do a union, and that is going to be again a narrow operation, because all you have to do is throw those values together and then count them. Okay, now finally, when you want to reduce, when you're ready to do the reduce operation, you will have to club together all the shipment values for each customer. Okay, so what you do is a join of these two RDD. Okay, and so look at this. Why is this part a narrow transformation, but this part is wide? Just think about that for a minute. Okay, why is this transformation a narrow dependency, while this one is has wide dependency? Any suggestion? You can type. Yeah, Tom says they have to have one-to-one correspondence. That's right, because when you do group by, okay, you have already ordered the customers by the records by the customer ID. Okay, so you don't need to do any more shuffling. You've already ordered them and grouped. That means added up the values. But here, this is an union, so all the results are jumbled up here. Okay, there could be records for customer 1 here in the first partition, and then there could be some in the third partition, fourth partition, and so on. So these need to be again sorted. Okay, so this is a wide dependency operation. So the main point here is the one type of operation like join can either have narrow dependency or wide dependency, and you have to pay a lot of attention to this when you are developing your Spark program, because wide dependencies are going to take a lot of time. Okay, there's going to be latency associated with shuffling all this data around. Okay, but narrow dependency transformations will be faster. So wherever you can help, okay, you try to use narrow dependency operation. Okay, so that's all I have to say about transformations. Now we will go to the the next part of RDD, which is resilience. Okay, as I said, RDD stands for Resilient Distributed Data Set. So what does resilience mean? It means that while you are doing your calculations, if a particular node or a rack or a switch dies, then you only recompute what was lost. Okay, you don't have to recompute all the results. So this is very well illustrated here in this figure. Let's say, yeah, this is the same Amazon operation. Okay, you've done a group by, map, and then a union, and then let's say you are about to do a reduce operation. Okay, you are trying to join these two RDDs, and when you're about to join the two RDDs, this partition is lost. Okay, so one main feature of RDDs is that they have metadata. They have metadata, and the directed acyclic graph, DAG, is part of the metadata of each RDD. Okay, so from the metadata of this RDD, you know the DAG operation that resulted in this partition, okay, in this data. So all you have to do is execute just that DAG, and you will. So that means you go back here, you find that you from the metadata of this RDD, you find out that the DAG for that RDD, which takes you back here, and then you compute this, restore this, and then you carry out the reduce operation. So just because you lost this partition doesn't mean you have to recompute this whole RDD. All right. So that's what is referred to as resilience. Okay. So now let me show you a simple code and related to the internal operations we have been discussing. Okay, let's say we are just doing a simple word count. Okay, you should be familiar with this code by now if you have been looking through the assignment. So this is average length is equal to the spark context dot text file. You give this file name, and then you are applying a flat map. This is the function. Okay, this is the flat map function. All it does is it takes each line and splits it into words. Okay, and then to the result of the map, flat map operation, you are applying a map function. Okay, which is this lambda. It takes each word and makes and emits key value pairs. The key is the word itself. The value is the length of the word. Okay, so and then you're doing a group by key. But let's stop right here. Okay, so you have created an RDD by taking a text file. Okay, reading in a text file, and then you are applying this flat map function to each row of the RDD. So what this flat map does is it splits up each line into words, and then you are applying the map function, which takes each word and generates key value pairs. Okay, so that is stage one. When you're writing a code like this, this is what you visualize. Okay, you have an RDD, flat map. You don't have to go across partitions. You just take each row, and you can think of split as putting commas between the words in a line, right? It just generates a flat map, and it sticks that the entire line in here. Only now there are commas between the words. Okay. What does the next operation do? It takes each word and calculates its length, and now it does a map. So let's say there are 10 words in the first line. So now you're going to have 10 rows, okay, one row for each word, and you will have key value pairs, which will be the word and the length of the word, okay. So now it should be very clear that this does not require any shuffling. Okay, so all of this are narrow dependency operations. The data flow from here to here. Okay, similarly, data flow from here to here. And then finally, we are doing group by key. So now you have a word like, I showed you an example, Abbott. It is here. It is also here. So you need to bring those two records to the same partition in order to count or in order to add up their values. Okay. So group by key results in wide dependency transformation. All right. And then in stage 2, once you have that, you are applying this lambda function which calculates the average length. Okay. And average. Okay. So that is stored in this RDD. Now, as I said, these are all transformations. Okay. Flat map, map, group by key, map are all transformations. So when you write this piece of code, you assign the result to RDD called average length, and you hit a return. Okay, Spark does nothing. It generates the directed acyclic graph. Okay, and it has a logical plan for executing this. It comes up with a logical plan for executing it. Okay, but an actual physical plan has not been submitted to the cluster yet, so there is no computation happening. The minute you type average length dot count, it goes, computes everything, and gives you the result. Okay, till that time, all these operations are stored as DAGs, and it is internally optimizing the computations and things like that. Okay, so count is an action. All these are transformations. Okay, so when you're writing, when you're doing your assignment, I want you to visualize exactly what is happening behind the scene. Okay. Okay. So very briefly, data frame is a huge step up from RDD. I'm not gonna. You're mostly going to be using data frame. So I want to tell you, give you some of the most salient points about data frames. Okay, data frame is again a generalized, sophisticated evolution on RDD. Okay, what it does, the main thing it does is it infers a schema from the data. Okay, so it is a data structure that has a schema behind it. That means you can bring all the power of SQL to analyzing any data stored in a data frame. Okay, so as you know, so you should try this out. When you create a data frame, okay, you can do, let's say you have a data frame called data. Okay, then type in data.print schema. It will give you the schema of the data that it has read in. Okay, and now it's as if you are working with a SQL table. Okay, you can do all kinds of operations on it. Okay, and then I've listed all the other important features of data frames. So you need to be aware of them also. But the main difference between an RDD and a data frame is that data frame infers the schema, and you can apply a lot of SQL-like operations or even SQL functions. Okay. All right. Any questions so far? I think it's been very quick. I'm going to quickly see if there are any questions. If not, we will move on to the machine learning library. Are there any questions? Okay. So, machine learning with Spark. A lot of you have posted, over the past few weeks, about Mahout. I think I think it was on the discussion for week 6 and 7 when we were discussing HDFS and Mapreduce and their applications. Mahout was a machine learning library, but it was developed for Mapreduce 1. Okay, it is not in use anymore. Nobody you should not be using Mahout anymore. There is no support for Mahout. Okay, you know that HDFS itself has evolved, and now you have Hadoop 3.0, which is Yarn, and you have the newer versions of Mapreduce and Spark, okay, running on Hadoop 3.0. So when Spark was developed, Mahout was, kind of deprecated, and something called a Spark Machine Learning Library, or MLlib, was developed, okay. And then later on, even that was replaced with what we now call Spark ML, okay. If you look at your Spark API, either in Python or in Scala, you will see, all the usual stuff, or the usual package structure, spark.mllib, and you will also have spark.ml. You should use spark.ml whenever you can. Not all functions in MLlib have been implemented in SparkML, but SparkML has better implementations of the functions that it has. Okay, some functions in SparkML still refer back to the older functions in SparkMLlib. Okay, that's just because people have not gotten to upgrading those functions. But just remember the history at Mahout. Please don't use Mahout. There is SparkML lib. Somebody is asking, let's see, XG boost algorithm is available in MLlib. I think it is available in ML. I don't know if it is available in it was available in MLlib. I have a list of algorithms. Yes, popular gradient boosted tree. Yes. It is definitely available in SparkML. I will talk about it a little bit. Chris is asking if XG boost algorithm is available in MLlib. It is available in SparkML for sure. Okay. All right. So let me quickly explain the features of ML, SparkML. These are features that are applicable both to MLlib and ML. Of course, you have the data frame. That's how you should try to store most of your data. But I will make some exceptions. There are some algorithms that don't work on data frames. You will have to use RDDs for them. Okay. You try to apply some, fancy clustering function to a data frame and it doesn't work. But you kind of know that algorithm has been implemented in Spark, then it's probably because it is in the RDD API, not in the data frame API. Okay, there are all those weird things still happening, but it's maturing fast. Okay, and the next important thing is a transformer. The transformer is an algorithm that takes one data frame to another. Okay, that's all. It transforms data into another. Now you know that when you have raw data, you cannot just send it to a model, right? You cannot start training a model with the data. You have to do a lot of cleaning and filling in the missing values and all that stuff. So those operations take place in transformers. Okay, you got to clean the data. You have to prepare the data, do some feature engineering. Okay, all of those are done using transformers. An estimator is what is used to estimate the model parameters. Okay, after you're done transforming your raw data into like a feature set that you want to train a model with, then you say fit, okay, and that will generate the model. Okay, a pipeline is how you fit together lots of different transformers and the estimators. Okay, so I have better visuals. Let me show you the visuals here. Okay, so I have two pipelines, one for training, one for testing. Okay, let's assume we are just doing some kind of a document classification. Okay, so the pipeline for document classification starts with a tokenizer. You just take all the text and you tokenize them, and then you do some hashing term frequency. Okay, that's just going to create a massive matrix with all kinds of frequency counts for all pairs of words and things like that. And then on that data, you're going to do logistic regression. Okay, so your pipeline is simply equal to an array of tokenizer, comma, hashing TF, comma, logistic regression. Okay, that's an array, and that you create a pipeline with that array. Okay, and once you do that, you do pipeline.fit and you feed the data, and it gives you a regression model as the output. Okay, so now for the testing, again you have to do a testing pipeline. Okay, so you pass the data through the same tokenizer hashing TF, and then what you do is apply the data, the transform data to the model. Okay, and it gives you the prediction. So here you say pipeline model dot transform, and it gives you prediction. Okay, so again here the pipeline has tokenizer, comma, hashing TF, comma, logistic regression. When you do a fit of the pipeline, you're going to get a logistic regression model. Then you set up a pipeline for testing. It's going to be tokenizer, hashing TF, comma, the model itself. And when you transform a given data, it's going to flow through this, and the output will be the prediction. Okay. So, is there any question about this process? It's all very structured and streamlined. Once you know this, you can train and test hundreds of models in a week. Okay, it's all very very simple to do. Okay, and then let's see. Here's the list of algorithms that are available in SparkML. Let me see. Did I list? I have not listed decision trees and with AdaBoost, but it is available. And the list is growing fast, so you should be able to look up the API documentation on Apache website, and you will see all the new algorithms that are available in SparkML. You also have neural networks, and I believe some framework for doing deep learning. Okay, so all of that is now currently available in SparkML.